Good morning, everyone, and welcome. I just take this opportunity and say it in bom dia a todos, bem-vindos, e buenos dias a todos, bienvenidos. My name is Sarah. I'm from the University of Trás-os-Montes, Alto Douro, and I will be your moderator for today's session. And it's a pleasure for me to introduce our speaker, Dr. Pedro Marques. This webinar, titled The Transferability of Machine Learning Methods from Precision Agriculture to Toxicology and Mutagenesis, marks the first session of the SEMA NY webinar series. I would like to begin by thanking the board members for organizing this initiative and Oscar Herrero for his technical support. As a reminder, the goal of SEMA New Investigators Group is to strengthen collaboration among early career researchers in environmental mutagenesis, and we are very happy to have you all here today. Before we begin, just a couple of quick notes. This session will be recorded and later uploaded in the SEMA YouTube channel. If you would like to receive an attendance certificate, please feel free to contact us via the Teams chat. You can also use the chat to post questions as the presentation develops, or wait for the end of the presentation to raise your hand on Teams. Now it's my pleasure to introduce Dr. Pedro Marques. Dr. Marques is a researcher specialized in remote and proximal sensing for precision agriculture with extensive experience in monitoring key crops in northern Portugal, including vineyards, chestnut trees, and olive orchards. His work focused on integrating UAV, satellite, and spectroradiometer data with GIS-based analysis to support irrigation management, crop stress assessment, yield prediction, and sustainable land management. He also has strong expertise in dataset creation, curation, and validation for machine learning, as well as in developing predictive models using multispectral, thermal, and spectral data. Today, he will explore how methodologies developed in precision agriculture can be applied to toxicology and mutagenesis. Please join me in welcoming Dr. Pedro Marques. Dr. Pedro, you have our full attention.
So, good morning, everyone. First of all, thank you, Sarah, for your nice presentation. And I want to thank the organization of SEMA for inviting me and giving me this opportunity to present my work. It's always a pleasure for me to present this work that me and my team developed along these years. In this presentation, and as Sarah said, and very well said, I will explain in this webinar how we can apply machine learning methods from the precision agriculture to the toxicology and mutagenesis. So first, let me introduce myself with a bit more information about my academic background. I studied computer engineering in the University of Trás-os-Montes, Alto Douro, where I have my bachelor and master's in computer engineering. And it was here in my master's where I have my first contact with remote sensing, in this case applied to chestnut trees. And then I have my PhD on agricultural production chains, also using remote sensing, however, in this case used for olive trees. So this is my academic background. And for my professional background, I already worked in some projects, all of them related with remote sensing for different kind of applications in many crops, in this case for vineyards, for olive trees. And in this case, at the moment, I am working as hire technician in a project that is called Vine and Wine. And in this, me and my team, we are trying to develop new remote sensing technologies to provide to the farmers technological solutions so they can perform a precision viticulture in their fields, in their vineyards. So let's now start the presentation. What I will talk about. This presentation is divided in these three main chapters. Firstly, I will introduce, because I know that you are not from the area of remote sensing, and of course I present some concepts, basic concepts of remote sensing, the kind of technologies that we can have, like platforms and sensors, and I will talk just a bit, a theory of machine learning. Then we will have some slides with practical applications that me and my team developed in the precision agriculture using machine learning. And in the end, I will show you a small video, like 5 minutes, explaining a scientific paper that I found where they apply machine learning in the mutagenesis area. It's not in the ambiental mutagenesis, but the concept it's the same. So I think it's a good video to show you. I made this video with the help of AI tools. So for me, it's more comfortable to talk about this area that it's not my area. So it's better for you and it's better for me. So let's try to understand what is remote sensing. And remote sensing is very simple. Remote sensing it's the acquisition of information about objects or areas without any direct contact with that object, which means if I take my smartphone and took a picture, a photo of, for instance, a leaf of a grapevine, that's remote sensing, because there are no direct contact between my smartphone and that leaf. However, if I'm using like a sensor that it enters with contact with the leaf, that's proximal sensing and not remote sensing. So this is the major difference between these two concepts. And there are many platforms that we can use on remote sensing. Starting from above, we have satellites, platforms that orbit the Earth around 800 kilometers. Then we have the manned aircraft or small airplanes. Then we have the recent technology UAVs or drones. And then we have the terrestrial equipment that are placed in field. Each of these platforms has their own pros and cons. The major difference between them is the spatial resolution. This is the major difference because as we are further from our object in this point of view, the higher the spatial resolution. For instance, when we have an image from a field using UAV or drone, we have an image with a centimeter pixel level, so it's very tiny. However, using a satellite and let's say the free satellites, this spatial resolution is from meters to kilometers. This is a big difference, and I'll show you some examples of these differences in the next slides. So this is some satellites that we have. This is European satellites. Each of them are for different purposes. For instance, this one, they are far away, it's for meteorology. And in the case of remote sensing, we use more this kind of satellites, the Copernicus. In this specific case, we used Sentinel-2 and Sentinel-1. There are much more satellites, like Chinese satellites. There are a lot of them, American satellites, Indian satellites, and this is only the most known satellites from the European Union. Then we have, beyond the satellites, we have the UAVs. There are two types of UAVs. The fixed wing UAV, like this one, it's like an airplane, and the rotary wings UAVs that are like small choppers or helicopters that we can use all of them to survey our area and take some pictures of our crops. Then we can mount in these UAVs different kind of sensors, and these sensors can operate from 100 nanometers until 4,000 nanometers, depending on the application we want to develop. In this case of remote sensing, we work a lot with these wavelengths. In this case, the visible region of the electromagnetic spectrum, and this near infrared. And why? Because is in this region where the light from the sensor, the leaf reflects a lot of that light. That's because of the chlorophyll. And I will show you a spectral signature of a leaf, and you will see that in this region the leaf reflects a lot of that light. So we use a lot this kind of information. And also we have the long wave infrared, that is like sensors that can give us the temperature, the land surface temperature, and the crop temperature of the leaves, that can also be useful in the remote sensing. Basically, there are 4 types of sensors that we can mount in the UAVs. This is the cheaper one, the RGB sensor, that operates in the visible electromagnetic spectrum, which means that it's lights that a human eye can see. That goes from 400 nanometers to 700 nanometers. That is composed by red, green, and blue. Then we have the multispectral sensors that beyond these 3 bands, green, red, and blue, we have another band that is the near infrared, and is here where the plant has a higher reflectance, and it's very, very important for information in the area of remote sensing. Then we have the hyperspectral sensors. This is the most expensive sensors. I'm talking about sensors that its cost is above 100,000 euros. So it's very expensive, but they can give to us the full information from, in this case, from 400 nanometers until 1000 nanometers about the crop. This is the full length of the information in this area. And also we have the thermal infrared sensors that give us the temperature, and it operates more far from the electromagnetic spectrum. So this is small sample of the behavior of the reflectance of a leaf. This green light, it's the behavior of a healthy plant. Here, as you can see, from the 700 nanometers to 900 nanometers, the plants reflects a higher portion of the light. This is the near infrared region, the region where we use a lot in remote sensing. And there are differences between, for instance, an healthy leaf and a dead leaf. There are differences between these. The majority difference is in the near infrared, but also there are differences in the visible lights. But the major difference is seen here in the near infrared. This is another example of spectral signature. This is 4 leaves. The green one, it's an healthy leaf. This is a normal behavior from the leaves that are healthy, and then we have the leaves with some kind of stress can be provoked by water stress or diseases. And as you can see here, there are huge difference along the electromagnetic spectrum between these 2 type of these two leaves. From the leaf pigments, they change a lot, the cell structure of the leaves, and in this region, when we see the water content of that leaf. And then we have the sensors that are mounted in the satellites. In this case, and as I said before, the big difference between the image from a satellite and the image from UAV is the spatial resolution. In this case, I'm showing you the Sentinel-2 resolutions that are the satellite that are most used in remote sensing, and can give to us images from 10 meters to 60 meters of spatial resolution, much bigger than the UAV, but it has their applicability. This satellite can give to us 13 spectral bands. They are here. Depending on our application, we can use more one or another. And the satellite passes by our field from in intervals of 5 days during all the year. So this is basically the platforms and sensors that we can have in remote sensing. Now I will show you the kind of products that we can have with this kind of technology. So this is images that were captured by UAV from a vineyard. This is a RGB image, which means that is visible light, what the human eye can see. And then we have here the vegetation index. These are the, let's say, in this area of remote sensing, the vegetation indices are the most used technique to different kind of applications, from disease classification, from water stress detection. We use a lot of vegetation indices. This is an DVI, the most known vegetation index, and the vegetation indices are basically arithmetic operations that we can apply to different bands. In this case, there are operations applied to the near infrared band, that band that I talked before, where the leaf has higher reflectance, and the red band, and can give to us this kind of information that we look here, and we can check, for instance, just look at this image, where the vineyard has higher vigor than other parts of our parcel, for example, these bottom parts. And also we can distinguish between vineyard and bare soil. In this case, the soil is the red region and the vineyard is in green. And also we can have this kind of information that is the land surface temperature and the temperature of all objects that are on our land, in this case vineyards, that are very useful, for instance, to studies that correlate water stress index, or to detect water leakage in the irrigation systems. These kind of information are very important. This is another type of information that we can have. I'm sorry, I passed the video. Yeah, this is another kind of product. This is called a point cloud. Basically, the difference between this information and the other information that we presented before is that here we have an image that is 2D, which means that has X and Y, and here we have a point cloud that has an X, Y, and Z. So it's kind of different. We can go around the vineyard and look for some spectral information that we need to use on our studies. That very useful, but very complex to deal with it, and we need a lot of computation power to produce products like this one. So in this slide, I show you the difference between spatial resolution, as I said before, between an UAV and images from the same vineyard from satellites. And as you can see, it's a huge difference. So here we have an vineyard with each pixel has 2 centimeters of length. And in this case, we have 10 meters of spatial resolution, 20 meters and 60 meters. It's very, very different. But for instance, if we want to make some study for a big region like Vila-Real, old district of Vila-Real, we cannot use the UAV because the scale is too large to use in UAV, so we need to use satellite imagery. This is again the differences between the spatial resolutions, and in this case the difference between vegetation indices and DVI from UAV and from satellite, but there are some similarities between them. And this is the major issue of satellite, that is the clouds. That's because the satellite orbits the Earth above the clouds. So when the satellite is visiting our experimental area, if there is clouds, this kind of information cannot be used because the pixels are contaminated with clouds, so that this is not a good information for us. And in the other hand, if we fly with UAV below that the clouds, we can have the information that we want. So basically, here until now, I showed you what is remote sensing, what kind of platforms there are, and what kind of sensors we can mount on these platforms. And these sensors can give to us a really lot information, huge data that we need to handle, and we need to find patterns and extract information that it's very hard to handle when there are like millions of pixels that we need to analyze. So machine learning can help us with this, because machine learning it's like a method that allows computers to learn complex patterns, and these help us a lot with big data. And basically, you can define machine learning in two groups: for regression methods and classifications, which means regression is when we want to predict some value. For instance, I want to predict the yield of my vineyard, that's a value. Or classification. Classification, it's when we attribute to a pixel or to our data set a class. For instance, class number 1, class number 2, class number 3, and not a value like the yield that is a continuous value. And independent of the area that we apply the machine learning, can be for remote sensing, can be for toxicology, for mutagenesis, for another area, the pipeline is always the same. It's always this one, that we have our data set, we train our model, here it's machine learning, we train our model with our data, where we say to the model, this is the values that you need to predict what I need to predict, and then the model make their prediction. And basically, I show here the most known models for machine learning. There are simple models like decision trees that are very simple but not so robust like the other ones. There are the random forest, XGBoost, support vector machine. The most known that we see in studies is the random forest, because they are this kind of methods. They are very versatile for different kind of applications, and they can learn very complex patterns. And the training time, it's moderate, so we don't need a lot of time to train these models. And to apply machine learning, the bases are all the same for all the applications. What I mean it's that workflow, it's always the same. For instance, I have here an example of a data set where I have 10 samples. Each sample has some features that describe the sample. And in the end, I want to classify the samples based on these features. I want to classify if it is class 1, 2, 3, 4. And basically what we do is to divide our data set, where we divide 70% of our data is used to train the model, to teach the model the patterns that he needs to learn. And then we have the remaining 30% to test the predictions that you learn from here. So basically, the model only see these data, these 7 samples, to train the patterns between them, and never see these ones. These ones are only used to test our model that are built during this phase. So this is the pipeline. And in this phase, when we are training the model, we need to pre-process our data, and I will talk a bit more in next slide what it is pre-processing our data. Then we train the models only with 70% or 80%, 65%. It can depend, but it's usually 70%. And then we validate the data with the remaining 30%. And when we find the best model that, or when we are happy with that model, we can use that model to make some predictions on the data that were never used, or the model never see that kind of data. So here I present the pre-processing of our data. This is for me the biggest, what is the most important in machine learning. It's not the model by itself, it's the data, our data. Our data, it's very important. How we build our data set. For instance, I made here some example of a data set to classify fruits based on these 3 features: weight, color index, and diameter. And there are basically 4 rules that we need to follow, which are: we need balanced data sets to avoid bias. And what it is, and this kind of stuff, it's when we have, and in this case I made in purpose, I have here my data set with 10 samples, and I have 7 samples of bananas, 2 samples of apples, and 1 sample of orange. So this is biased because there are a lot of samples describing what is a banana, but a few samples to describe what is an apple and orange. We need to avoid this. We need to give basically not the same number, but approximate same number, an approximation, same samples for each class to teach our model with the same rates. Our model must be a representative data. This is common sense, like it must reflect real conditions. The data volume is very important in machine learning. That's the big issue of machine learning. We need a lot of data because the methods need this late data to learn the patterns, to build more robust models that we can apply on different areas. However, then we have another issue, that is the quality. So we prefer quality over quantity. This means that yes, we need a lot of data, but quality data, because if we give bad data to the models will not learn what we need to predict, and that's a big mistake in this area of machine learning. And we need to avoid errors and noise. For instance, I have here an sample of orange, and this orange has 600 grams of weight and 25 centimeters of diameter. So this is an error. An orange will not have this kind of features. So we need to look to our data set and find these errors. There are always errors in our data set, and there are always noise that will confuse our models. And this is the biggest deal of machine learning. So basically, just to summary all this information regarding machine learning. So machine learning learn patterns from our data. So our data is very important, and the quality of the data, it will strongly affect the performance of our models. And the workflow is generic, which means that, of course, that I cannot apply a model that I developed for remote sensing, for example, for mutagenesis, because it's different. But the way that we train the model, the way that to create the model, it's always the same. The principles are always the same. So it's like the workflow that we need to follow is it's basic for let's say that. And now I will show you. Let's jump to the practical applications. That was the theory part, and I will show some examples of how me and my team applied some machine learning in applications in the precision viticulture and in the agriculture. I divided the slides in machine learning used for regression, which means we want to predict a value, and for classification, which means we want to classify. In this case, we create blocks of 5 meters in vineyard and extract some information like vegetation indices and try to estimate biophysical parameters. This is some of the vegetation indices that we estimate on this kind of data. And then we develop methods to estimate the leaf area index, the pruning goods, and yield. The models which had a good accuracy with a coefficient of termination above 0.8, and then we can produce maps like this, where we can give to the farmer simple maps like this where you can see where for instance, with this kind of information, the yields, the zones of the vineyard that has the more potential to be productive. In this case, this upper part of the vineyard. This is another example of application of machine learning in remote sensing. In this case, is to predict yield using satellite imagery, and has the spatial resolution of this kind of platforms are very big. We cannot predict the yield like we perform here. So in this case, we predict yield in all the parcel of the vineyard. This is a mosaic of the satellite Sentinel-2. This is like almost Villarreal, all the district of Villarreal. This is the NDVI map and the temperature mosaic with some crucial information. And then we developed 6 machine learning models to estimate the yield depending on the months of the year. And we have good results between, I'm sorry, this is in Portuguese, between June and August, where the models have a coefficient of termination above 0.9 with very low error. And these are the main results, the predictions of the machine learning models. And for instance, in August, that was the best model that gave us the best approximation of our estimation. In 500 tons of grapevine of the production, the error, it was only 6 tons, very low. However, in June, which means that it's 3 months before harvest, the model also can estimate the yield with only 10 tons of error. So this kind of information is more early than August and is very useful for the farmer. And now we have the classification models where we classify In this case, we are not predicting values, but classify our image. In this case, we train a machine learning model, or in this case, deep learning models, to say to us where the vineyard is, which pixels belongs to the vineyard. This is some result of some samples that we have from different methods, and this is final result. So we give the model this a mosaic, and the model gives to us this kind of information, only the pixels that belong to the vineyards. This is another type of applications that we developed, that is the classification of diseases in vineyards. In this case, using pictures, photos of the leaves, using a smartphone to detect and classify the diseases. The four of the most common diseases found on the the vineyards, with a high accuracy of 97%. And lastly, I show you this classification of agricultural fields, also using machine learning, of course, where we have fields that has three type of crops. In this case, we have here in the middle part an olive orchard. Here we have a vineyard, and here we have a nectarine orchard. This was made by hand. This is annotated data. That is what we want the machine learning models to give to us. And we classify this image in 5 classes: olive trees, nectarine trees, vineyard, bare soil, and the shadow. This is the way that we train the models. So we created small clusters that was random along the images, and then we attribute a class to each cluster, these big ones, and then this was the test data set, and then we create just small samples of each class and give to the model saying, okay, this is a sample of the class 4, this is a sample of class 3, this is a sample of class 1, and then the model has the ability to predict all the mosaic and classify the image. This is the results. We trained 4 different models. The model with best performance was the random forests, and as you can see, this result is very similar to this one that we wanted him to give to us. This is annotated by hand, and we have an accuracy of 91%, very good accuracy. And we have the opposite models that have lower performance, in this case naive Bayes, where these models have struggled dealing with distinguishing between vineyards and olive trees, with some mixed pixels over here. And in here we also struggle between nectarine trees and olive trees. So it has 79% of over accuracy, and we can see that big difference between this image and between these one that are more clean, let's say. So to now this part, I'll present, as I said in the beginning, a small video of a study that I found. I like the study where they used machine learning to train models to predict the mutagenicity, not in the environment, but the principle, I think it's the same. I made this video with some help of AI tools. The article is related with optimizing machine learning models for mutagenicity and prediction through better feature selection. And I like this paper because they go beyond the machine learning models. They talk a lot about the quality of the data, and this is the big deal of machine learning. This is the pipeline that they use to predict this mutagenicity. Basically, they used 4 features to train the model, and then they split their data set. In this case, I think they used 80% of data to train the model and 20% to test. And then they used 5 different machine learning models to train this data and to give to find the best model that predicts better the mutagenicity. So let's see the video, and then we discuss a bit the video.
All right, let's get into it. Today, we are talking about a major breakthrough in how we use AI to protect us from potentially dangerous chemicals. But here's the twist. The big secret wasn't some fancy new algorithm. Nope, it was something way more fundamental. Just better data. This is the story of how scientists taught an AI to be a smarter scientist itself.
So it all starts with this one huge question. I mean, think about it. If you're developing a new drug that could save lives, how do you make absolutely sure it won't have some hidden dangerous side effect? How can you possibly know if a brand new molecule has the potential to do harm right from the very beginning? This isn't just theory. It's one of the biggest challenges in chemistry today.
To really appreciate this new solution, we have to understand the problem they were up against. For decades, spotting these dangerous chemicals has been a really high-stakes game, and honestly, a very, very slow one.
At the very heart of this problem is a specific kind of danger we're trying to avoid: mutagens. Now, a mutagen is just a chemical that can cause a genetic mutation. In other words, it can actually damage our DNA. And, that's something we definitely want to stay away from.
For years, the gold standard for spotting a mutagen has been something called the Ames test. It's super reliable. But, and this is a big but, it's got some major issues. It is slow. It is expensive. And, most importantly, you have to physically have a sample of the chemical to even run the test. This creates a massive bottleneck if you're trying to screen, say, thousands of potential new medicines.
So to get around that bottleneck, scientists did what you'd expect. They turned to AI. The dream was to teach a machine learning model to do the exact same job as the Ames test, but do it instantly and completely in a computer.
The first idea they had was pretty intuitive. If you want an AI to spot a dangerous molecule, you just show it what the molecule looks like, right? You give it a kind of chemical mugshot and tell it, okay, learn what the bad guys look like. Now, in the machine learning world, this mugshot is called a molecular fingerprint. It's basically a long string of ones and zeros that digitally represents the unique structure of a molecule. It's a fantastic identifier for sure, but just like a real fingerprint, it doesn't really tell you the whole story about the suspect. And that right there was the problem. When they used only these structural fingerprints, the AI models were, well, they were okay, but they weren't great. As the researchers themselves pointed out, the accuracy kind of hit a ceiling, somewhere around 80 to 85%. Now, that sounds pretty high, but when we're talking about something that could damage DNA, being wrong 15% of the time is just not an option. The AI had hit a wall. So what gives? Think about the AI like a detective. It was good at solving the easy cases, but the really tricky ones just left it stumped. It became pretty obvious that our detective was missing some really crucial clues. And this brings us right to the heart of this research. The big idea, the breakthrough, wasn't to go out and find a brand new detective or, build a whole new algorithm. The idea was to give the detective they already had a much, much richer case file, one that was packed with 4 totally different kinds of clues.
So clue number 1 is the one we've already met, the molecular fingerprint. This is that basic mugshot, the molecule's fundamental structure. It's the foundation for the whole investigation.
Okay, clue number 2 adds the suspect's physical stats to the file. We're talking about the molecule's properties, things like its weight, its size, even its solubility, which is this value called log P. That basically tells the AI how the molecule behaves in fatty versus watery environments, which is super important for understanding how it might interact with our bodies. This is all info you just can't get from the structure alone. The third clue is kind of like giving the detective a list of known criminal calling cards. These are called structural alerts. They're specific little pieces of molecules that experts have already flagged as suspicious because they show up in mutagens all the time. It's like telling the AI, hey, if you see this pattern, you need to pay extra close attention. And the fourth clue, well, this is the most advanced one. Think of it like a deep psychological profile of the molecule. Using this really powerful simulation technique called density functional theory, or DFT, the researchers could calculate things like the molecule's quantum energy levels. This gives the AI this incredible insight into the molecule's reactivity, basically where its electrons like to hang out, which tells us how likely it is to mess with a strand of DNA.
Okay, so our detective now has this complete 4-part case file. The big question is, did it actually work? Let's take a look at the results. First things first, we need to know the record we're trying to beat. The previous best-in-class model was called Protox 2. It achieved an accuracy score, which we measure as area under the curve, or AUC, of 0.90. Just think of AUC like this. 1.0 is a perfect A+, and 0.5 is just random guessing. So, 0.90 was the score to beat. Now, what's so cool about this is it shows just how thorough these scientists were. They didn't just pick one algorithm and cross their fingers. No way! They tested 120 different combinations, trying out different models like support vector machines, random forests, neural networks, and pairing them with different sets of those clues to find the absolute best detective for the job. And they found it. The winning combination achieved an AUC of 0.93. That's a new state-of-the-art record. Now that jump from 0.90 to 0.93 might seem small, but in the world of machine learning and chemical safety, trust me, that is a huge leap forward in predictive power. And this chart right here just spells it all out beautifully. This is tracking the best algorithm they found, a support vector machine. With just the structure, the mugshot, it scores a 0.84. But watch what happens. You add the molecular properties and bam, it jumps to 0.91. Then you add the structural alerts and it hits that record-breaking 0.93. I mean, this is the smoking gun. Every new layer of data just made the model smarter. So let's wrap this up. What's the big idea here? What's the key takeaway from this whole investigation? It's this simple but profound idea. Better inputs lead to better outputs. The hero of this story wasn't some wild new deep learning model. In fact, the algorithm that won was a classic, the support vector machine. It didn't need to be replaced, it just needed a more complete picture of the problem. What this research proves is that giving your model richer, more meaningful data can be even more powerful than just building a more complicated algorithm. And that has a real impact, making drug discovery faster, cheaper, and ultimately safer for all of us. And this leaves us with a really fascinating thought to chew on. We all get so excited about the newest, biggest, most complex AI models. But this study shows that sometimes the real breakthrough, the real genius, comes from just looking at the data itself. So it makes you wonder, what other giant scientific problems out there aren't waiting for a better algorithm, but are just waiting for us to give our AI a better set of clues?
So, just to finish, we saw with this video what I said during the presentation, that sometimes the problem it's not the machine learning by itself. It's not the model, it's the quality of data, and the quality of the data, it's very, very important, and that's quality of the data we need to give to model this kind of information, and we need to pay attention to our data set, look at the data, find errors, give representative data, not biased, and for sure the machine learning models will learn the patterns and give us the good results that we want. So that's the end of my presentation. I hope you like it, and now I free for your questions to answer if you have it. Thank you.
Thank you very much, Dr. Pedro Marques, for this insightful and engaging presentation. And now the Q&A session is open. So if you would like to pose a question to Dr. Pedro regarding his presentation, you can raise your hands on Teams. You can use the chat box in Teams to pose the questions for Pedro. So in the meantime, let me just check. Okay, in the meantime that the audience is thinking about the questions, I would like to pose one, Pedro, if it's okay.
For sure, for sure.
So what do you think is the biggest challenge when transferring machine learning models from agriculture to toxicology?
The biggest challenge is it's the data. It's always the data. So when we have like imagine an Excel file with 1 million samples, that's very hard to a human to see sample by sample and check if there is an error or check if the value it's not the correct one. That's the big deal of machine learning, because machine learning needs a lot of data, lot of data to learn that patterns. But this data needs to be quality data, and that's the big challenge of machine learning nowadays. Turn our information into good information, and that's the ex libris, for let's just say, of machine learning.
Okay, thank you. I think we got a message that, okay. Thank you, Peter. Thank you, Peter, sorry, Pedro, for, for your feedback. We got a question in the chat box. I'm going to read it, okay? So, for researchers who are new to machine learning, what will you recommend as a good starting point to begin applying these methods in environmental science? So it's from Alba.
Okay, a good start point is to check data sets that already exist, public data sets that are used for machine learning, that are already trained, and that they are already tested. So to see how the information is organized, how a good information is organized, then we apply this organization on our data and try to. This is the, I'm always saying the same, but this is the biggest deal. We need to look to our data and understand. We need to understand our data and try to give to the machine learning models the best features. Not all of them, because there are some features that are not relevant to our purpose, but the best ones. And then we can use, when we have our data set, okay, this is the best data set I have, we can use, for people that are here that are not from the area of machine learning and so on, you can use new technologies like ChatGPT. These kind of tools help us a lot, where you can give him not the data set and explain the problem. I have this data set, I want to predict this value, how I train my model, what I need to install, what program I need to install, and give me like a small course of 1/2 an hour. How can I install it? How can I take my data and train a model and do some predictions? So this is basically the same, the thing that I recommend new people to do.
Okay, Pedro, thank you. So it's all about the model, all about the data, quality of data, right?
Yes, yes.
So
the quality of data, it's the biggest, the most important thing.
okay, so we have here a question about quality of data from Blanca. She says, thank you for the amazing presentation. How can we be sure that our data has enough quality to apply machine learning methods? That's a good one.
Yeah, that's a good question. For instance, to see if our data is biased or not, we can see the histogram of our data, and we can check the distribution of the values, if it's skewed or not, if it follows a normal distribution. If it follows a normal distribution, they are good data. Another thing that we can do is look at the samples. Look at the samples and eliminate errors, noise. If there is some value that we don't have sure if that value is correct, it's better to remove it. If you're not sure of that value, remove it, because that will be an error that will propagate for the model, and the model will give us bad information, bad predictions. And let's say the last one is the size of our samples. Imagine we need, as I said, we need to split our data set, 70% for training, 30% for test. So imagine we have a data set with only 10 samples, which give us 7 samples to train, 3 samples to test. We can't do that because it's low quantity of data. It's only 3 samples to test our method. So I will say the minimum amount of samples that we need on machine learning, it's like 100 samples, and we use 100 to train our model and 70 samples to train and 30 samples to test the model. This, for me, this is the minimum samples that we need to provide to the machine learning models. And of course, it also depends of the complexity of our problem. There are some problems that we need more than 1,000 of samples when there are where the patterns are very similar between categories. So in that case, we need or more features, like in that case of the fruits, we had weight, color, and diameter. If these 3 categories or these 3 features are not the sufficient to distinguish between fruits, we need to add more information, more features. So yeah, this is basically how we can check our quality of data.
Okay, so you need also time for training,
Yes.
for machine learning, right?
Yes.
So in this note, yeah, sorry, please.
You are saying the next question, how much do we need to train the model? It depends.
Yes, and also does the PhD student has enough time during the pre-doctoral stage?
Yes. It has time to train the model. Depending on our application, the models can vary a lot. Taking those two type of machine learning models, there are the regression models and the classification models. The classification models usually takes more time to train than the regression models, because we are predicting a value and not categorizing it. So it's different. And it depends on the complexity of our data. For instance, that example where I show the algorithm to train where we train the algorithm to detect only the vineyards, the pixels belong to vineyards. Each model can take like 3 days to train. 24 hours by 24 hours. The computer always turned on. If a computer is accidentally shut down, we need to start over. So yeah, in this case, we need backup power. We need a supplier to the computer to avoid this kind of situations. And that's, let's say the model that took more time to train was like 1 week, no more longer than that. But that's the extreme, the extreme situation that we have. The most common are, for instance, that models that I show you that predict yield. It's like, let's say 10 minutes, 5 minutes to train the model. But also depends the way that you train the model, because the models has different kinds of configurations. And when we train the model, you don't need to use all the configurations possible. You need to focus only that configurations that are more useful for your problem. So in that part, I would say you need the help of, for instance, ChatGPT, and ask ChatGPT like, I have this problem, and I want to use a random forest. What kind of configurations do you think that is the best ones to train my model? Because this training process can take from 5 minutes to 1 day. And it's unnecessary because we need to focus only the configurations that we need to make our predictions. So yeah, that's more or less the time that we need to train the model.
Okay, so it's doable in the PhD pre-doctoral stage.
Yeah, yes.
So, okay, if I don't know if the audience is still thinking about the questions, I have another for you. Oh, sorry, just got in.
No problem.
I know, it's just thank you for your nice response. It's not a question. So, Pedro, I will pose a question. Which emerging machine learning techniques do you think is the most promising for mutagenesis?
Let's say random forest is always the best one in most cases. It's like a battle between random forests and XGBoost. Sometimes XGBoost models can outperform the random forest. However, the time we need to train that XGBoost models are bigger. We need more time to train that kind of models. But there are some new because machine learning. This is not so recent. This is a subject that is already talked in literature for quite a bit of time. And there are some new methods that are searching, like deep learning models that are even more complex than the machine learning models. There are now the one thing that we call the transformers. That is basically you take a model that that was trained for something and made some modifications and apply to another thing, because that model is already optimized. That's a big advance, because how here in our team, one of my colleagues applied this kind of technique and used like a machine learning model or a deep learning model that was basically trained to detect some anomalies in medical imagery. And then it took the same model and that's what they call transformers, and transformed in the precision agriculture, where it changed only the classes and some features, because the model is already optimized. And this is the biggest jump, because we don't need to train the model. The model is already trained. We only need to modify some classes, some features that the models have, and apply wherever we want to apply.
Okay, thank you for this feedback. So if there are no more questions, I'll just give you a couple of seconds.
Okay.
Okay. So if there are no more questions.
No.
Oh, sorry.
No,
yes,
no. I
ahead.
think we can finish it.
Okay. Yes. So yes, thank you again, Dr. Pedro, for your presentation. On behalf of SEMA New Investigators, I would like to express our sincere appreciation to you, our speaker, for sharing your work and perspectives with us today. I would also like to thank all attendees for joining and participating in this session. As a reminder, the webinar has been recorded and will be available soon at the SEMA YouTube channel. And again, if you need an attendance certificate, please contact us via the chat box in the remaining time. We are also excited to announce that more activities will be coming soon as part of the SEMA NY initiative, and we hope to see many of you again in future sessions. Finally, we also hope to meet some of you in person at the upcoming event, the 30th scientific event of SEMA in A Coruña this June 10 to 12. Thank you again, and I wish you all a wonderful day.
Thank you.
Thank you to all of you. Thank you, Sarah, especially.